Now let's start with Professor Amir, third lecture. So thank you.
Okay, thank you. Let me start my last lecture. And today what I'm planning to do is to give you some realistic examples of everything I've been saying in my two first lectures. And so the first one, I tried to give you a sort of phenomenological approach to some superconducting devices. And I tried to convince you that these guys can really show some sort of macroscopic quantum mechanical phenomenon as a proposition of Schrödinger-like states and things like that. So, and then these sort of devices, they must be very small, but not small enough to be completely separate from their own environment. And so they are always strongly coupled to some sort of realistic medium. The thing is that, so in a sense, we can never get rid of dissipation, get rid of some sort of coupling to the external world. And so we have to go with these two things. On the one hand, we have the genuine quantum mechanical state, and on the other hand, we have dissipation. And in my second lecture, I showed that dissipation tends to destroy quantum mechanical effects. So then, if we try to use that, for instance, in any sort of technological application, we need to understand how to control these sort of very drastic dissipative effects. And so then I showed you that in many applications of this simple phenomenological approach for quantum mechanical dissipation, we could, for instance, say that damping tends to destroy quantum mechanical autonomy, destroy quantum mechanical coherence, and so. What about the experiments? Can you really show some sort of realistic results corroborating those sort of predictions? And the answer is yes. And so what I'm trying to do today is to show you some experimental results, many of them. Of course, I'm not an experimentalist, so I'm not going to tell you about the setup for these experiments, but I will try to aim at these very particular features of these experimental results that corroborate those that physics I've been telling you about. So first, remember that we were playing a sort of Johnson junction, and when the phase is taken as a variable, and then I was telling you about the autonomy of this variable, the phase variable of the, so that's the phase difference of the wave function, the superconducting wave function through the terminals of the junction. And so there's this sort of quantum mechanical autonomy, but we can also have thermal activation at higher temperatures. So everything I presented here was zero temperature. So all these quantum mechanical effects, they were computed at zero temperature. And but you can also try to generalize those to finite temperatures. And then we have some sort of crossover from these quantum mechanical regime to the thermal activation. And so that's the sort of picture I showed you, if you remember. This guy here is the rate of autonomy out of these net stable well. And so I take the log of the inverse of this quantity, all that minus 1. And that's what is called this escape temperature. And that's a paper by John Clark and collaborators in Science. Very old paper, that was back in 1988. So that was the first signature that people were really measuring this sort of a phenomenon. Then we see that for high temperatures, we have something which is the Arrhenius factor, so the thermal activation. And then, as you start to lower the temperature, you tend to make it flat. So this is the result I told you about when you have the influence of dissipation. But for zero temperature, this result tells us that we have a finite decay rate from this stable situation. Classically, you would have this guy down to zero, so there will be no transition. And then we start to increase the temperature, and then we go over the barrier. The thing is that then we start deviation from the classical regime, and in the end, we have this flattening the curve in such a way that we cannot say that really what you're seeing is some sort of freezing of any sort of width, representing, for instance, the statistics of jump from one side to the other of the well. So that's what happens in this sort of system here. So we have this classical regime, quantum mechanical regime, and if you remember, I told you about the model that we used at junction, and that junction was replaced by a capacitor, resistance, and the capacitance, the resistance, and the junction itself. And in this case here, what you can do is to change this parallel resistance. So there's this shunt resistor. You change it. When you change the resistor, you change dissipation. So we can really control this guy here, this flattening, and see what happens. That's, for instance, this result is for an infinite quantity factor. So zero damping here. Then, as we start to increase damping, we lower this point here. So it will become more and more classical. So that's what happens. We start to change dissipation, and then it starts to act in a way that we tend to destroy this quantum mechanical turbulence. So that's for the junction. And then another one was the squid ring. You remember that the squid was the ring closed by a junction, and we could control that, all these stability configurations by changing the external flux. And so we can do something like this. For instance, we can keep this guy stable, and then we have a more stable one. And so that's a sort of picture that we can get, just changing the external flux. Okay, so when you do that, of course, later, actually next, I will address the problem of tunneling from one of these minimum to the other one, actually coherently. But this time, I will tell you about the results of the sort of photo absorption of this system here. So I have exactly the system I presented you. I presented to you last time. And so what we do is to shine microwave photons in the system and see what happens. And see, for instance, that we start in this initial state here, and then we have two choices. We can either make a transition to this state or to the other state there, depending on the frequency that we have. And so the thing is, tuning this external flux, we will change the height of the barrier and the relative position between these two minimum in such a way that this state here and this state here, they will cross. And when they cross, you can open this sort of gap of energy there. And what you can do is to start the initial state here, and you shine light on it, and then you would like to make a transition like that, to this dark line to the background. And then what happens is that as you change your external flux, you can either cross it here or there, and then you have two peaks. And these two peaks is the evidence that we really have quantum mechanical states related to the flux. So it's that's what we're talking about. That these guys we can really think of as these electromagnetic potential, as some sort of potential that we can quantize the motion of these coordinate, namely the flux. And so that's exactly what happens here. So then we're really talking about, if you want to look at this in terms of the picture I showed you, vortex lines. What we're talking about there is a sort of excited state of the vortex itself. So it's not a vortex only jumping, but the vortex, some excited, quantum mechanical excited states of the vortex line. So that's the sort of picture that we have for this system here. And another example is, again, the squids. But this time, what we're doing is really to change the flux in such a way that we have the bistable potential. And when I showed you about the spin boson Hamiltonian, I also showed you that we can approximate that for low damping to something like Bloch. Something like a spin in the medium, and that spin would be described by Bloch equations. So we are very close to the sort of NMR experiments. What these guys did was to change the external flux in such a way that we have this bistable potential. And then we can see what happens. Exactly the same way that, for instance, we have here a microwave line. So it's acting like an external pumping for the spin in a sort of external field. So that's exactly the NMR experiment we've been doing. Actually, many people talk about these sort of experiments here. For instance, to observe rock oscillations, random interference, and things like that. So you can observe exactly these same sort of things in a system like that. So what I have here is a squid. Actually, the squid is right here. It's a 3-junction squid. And so we can also change the external bias in such a way that I have a bistable potential. And you see here, that's exactly the result that we would expect from a quantum mechanical spin in an external field. So again, that's another evidence that everything that we've been saying about these systems behaving quantum mechanically, it's true, and it really makes sense. Third, let me go back to the other example that let me remind you of that picture of the Amir lattice in the case that we have a type 2 superconductor, in external field, we have the penetration of these vortex lines. And then, again, it depends on the sort of the relation of the penetration depth to the coherence length of the superconductor. Then we can have type 1 or type 2, and type 2 is when you have these, all these vortex lines penetrating in the center. Okay, so, but one important thing here is that vortex motion generates dissipation. Why? Because if we start with this vortex in a superconductor and we have a current crossing in a perpendicular way to the vortex line, what happens is that you generate a Lorentz force. And this Lorentz force will tend to displace the vortex. And when you displace the vortex, you change flux, phi dot, and that's voltage. So then, if you have this sort of thing happening, you can generate dissipation in the system. It will be very important for the interpretation of another experiment I will tell you about soon. But what happens to these vortex lines? These vortex lines, they are usually a pin. We have impurities in our system. For instance, if you have this sort of copper oxide planes in high C superconductors, then you can have, for instance, impurities. They will pin the vortex line. And actually, it's very important for technological applications, but if you want to have a sort of train levitating or any sort of object, you really need these sort of things to take place. Otherwise, the vortex will be moving around and you cannot stabilize the position of your system on the top of the magnet. So then, what we have here is that pinning is something very important. And for instance, another way to pin vortex lines, we can just have vortex in the direction parallel to the planes, and you can make a bombardment of this material with sort of external ions, and then you create sort of cylindrical region where you can get all these. So you have many impurities there, these columnar effects, and then you have pinning of vortex line here. So these are three examples of the way you can pin vortex lines. Okay, so I have a very complicated equation because I told you about something like Hall effect and Magnus forces and all that. And then I gave you a very complicated structure for the motion of a vortex line in a superconducting sample. But this time, I will try to make it simpler. So that sort of variable represents collectively transverse displacement of the line. So the line is doing something like that. And so that's the picture that we have. And then this guy is spinning all these lines that they can be pinned in the sample. And then, so it's pinned by this external potential, damping, we know that many origins for this damping. And so you have this elastic energy distortion of this line and some sort of inertial term, right? So that's the equation that we have. That's exactly the equation for the random particle except for the fluctuating term. And on top of that, we need to remember that it's now a line, it's not only a particle. Or the vortex is not completely still and it is distorting, so it's not fixed. And then, so we have this elastic term there. And what happens now? What sort of experiment do we know about these systems here? Well, okay, let me just give you the sort of dynamics that will take place. So I have this external potential, the new potential in the previous slide. And then you have this line, the elastic line, and this elastic line can be distorted. It can jump to the next minimum, depending on the size of this part coming to the minimum of lower energy. What happens is that this line can either shrink or expand. It depends on the balance of energy that it will gain coming to this new minimum and the elastic energy of distortion. So that's what happens. And then, if you have the critical size for this line on the other side, it will tend to expand. So then you have the transition from the line from this configuration here to the new configuration there. Good. So, but you know, the dissipation tends to inhibit these quantum mechanical effects. That's exactly what we've been addressing on this line. Now, what happens here? We have this sort of high TC superconductor, yttrium barium copper oxide, and we have a thin film of this sort of material. And as I told you, when we have a motion of vortices, what happens is that we generate dissipation. So in a sense, if we try to measure the resistivity of this superconducting material, right, what happens is that depending on the vortex motion, you can have something like this. And that's very interesting because, you know, as we start to increase the temperature, right, if you increase the temperature, you're right here. But now, for very low temperatures, you see what happens. You see that you have many different. Okay, let me show you exactly what happens to these vortex lines. For very low temperatures, they try to reach a sort of stable plateau for the very, very low temperatures. So for very low temperatures, this number is huge, so we're going into this direction. So that's exactly the signature that we have for vortex lines trying to, because for low temperatures, you see that this resistance starts to grow. to go up, and you increase drastically the resistance, but you have the main vortices moving around. As they move around, you have this so-called flux flow. And opposite to that, you have the quantum mechanical creep, which is the that motion that the vortex line will tend to leave these set of impurities and jump to another configuration. So the thing, once again, is pointing in the direction that for low temperatures, you have the motion is much harder for the vortex line. They will tend to be pinned, but you always have some sort of finite probability of quantum mechanical tunneling of the line. Not like in the high temperature regime, but still you have this sort of plateau taking place there. And the same sort of thing for the relaxation of the magnetization of the system. Because again, as time goes, passes, you see that what happens to the relaxation. And in this case here, you have the relaxation time. And again, for very low temperatures, you see that you have the freezing of the relaxation time. And now, for higher temperatures, it decreases. So that's exactly the sort of thing that we expect. So the lines will make a transition much more easily for higher temperatures. That's complete thermal effect. Right. Another one is, again, what I'm talking about now is a film and a junction, and we have many vortices. And so, for these ultra thin current carrying superconducting bridges, we have that's the dependence of the potential and the current that we can transport here, and that's the potential generated, across the junction. And so that's the behavior for high temperatures, and this one here is the behavior for low temperatures. And you can see that n is a function that depends on, it's a number that depends on the S exponent here, and that depends on the temperature and so on. And you see again, same sort of signature, that as we start to lower the temperature, you reach these 0.8, for instance, and that's exactly this straight line there. So we tend to freeze the slope of these lines for very low temperatures. And again, it's a signature of that freezing from the very beginning. That's pointing in the direction that we have quantum mechanical tunneling of all these unstable configurations. And then here again, you see these results, they show the same sort of behavior for different sizes or different temperatures and sizes of the junction. Right. Okay, so now we can think about
For these results in the previous one, do we have some kind of analytical law to describe very well this behavior?
Yeah. Yes. They all depend on. The point is that what you have to do is to apply the same sort of model I showed you. Actually, it's much easier because these guys are very thin. So I would really have sort of concave vortex line, so it's like this. So it's much easier to deal with. So I can really apply all these machinery of quantum mechanical damping, acting on quantum mechanical effects, and you can, apply, of course, these sort of superconducting systems, and then you can describe that. All approximate, of course. But these are very tricky systems that have many other things taking place there. You have to be careful in interpretation of what's happening. Now, superconducting qubits. So we're talking about these tiny devices that really show quantum mechanical effects, and now we can say something about the effect of dissipation on them. So we can try to reduce the effect of dissipation in order to extract some useful information from these devices. And then, what do we need if you want to talk about these the application of these systems to the QNets. These are the DiVincenzo desiderata, so to speak. So we have these well-defined two-state systems, accuracy in preparing the initial state, long fixed coherence, about 10 to the 4th coherent operations for these within the coherence time, and controllable effective fields, and quantum measurement and readout of the quantum information. So that's what we want from these tiny superconducting devices in order to use them in, for instance, computer memory. Right, and here we have something else. Now we will replace, of course, the main candidate to that is the squid ring or Josephson junction if we operate that at very low temperatures, and of course we restrict ourselves to a couple of states, so we can define a two-state system. And then we replace those by spin matrices and coupled ones, and with an external bias. So of course, we will always have to control these devices. So that's the sort of equivalent model that we have for interacting spins. So, and these bits, they must communicate, of course. And now, so who are they? First, we, for instance, we have this flux qubit, which is this, it's exactly the squid when I have this bias of phi naught divided by 2, then I have a bistable configuration. If we have a bistable configuration, we can replace that awful potential by something like this. And that's exactly what you can do. You know, you have something like the sigma z and the sigma x. That's exactly what I use in my spin Boltzmann deployment, right? So there was this 2 minimum, plus and minus, and the system would oscillate from minus to plus. And this guy here was the one allowing that to take place. That was a sort of transverse field. Then it would jump from one place to the other. One value of the spin to the other. Now, that was the flux qubit. Now we can also have the charge qubit. And the charge qubit now is exactly that same Josephson junction that I showed you before. But now, instead of what you're going to use now is the so-called Cooper pair box. Because what you're saying is that there is this phi dependence, but now we'll control the charge as before. We have this gate charge, I'm starting to change it, and then when I have this value of one electronic charge, you can open a gap. So we can reoperate in this region here. So we have a two-state system again. And so that's another candidate to be used as a qubit. Right? So the first one was the flux qubit. The second one is the charge qubit. Again, you know, it's, that's exactly a description of what we have of the system. So these are the number of Cooper pairs on one side and the other side of the barrier. And then you have something very similar to the description of a particle in a periodic potential in a one-dimensional solid. But now the interpretation is quite different, right? You know, we're talking about the number of Cooper pairs here, there, and on and on. And of course, we're playing about this, we're thinking about this n equals 0 and n equals 1 as up and down states. So that's the Hamiltonian that we have for the charge qubit as well. Something very similar to the formal description. And okay, I can do something else. If I want to control that, I want to control the system, this Josephson energy here, I can control that by replacing my junction by a squid with two junctions. So a squid with two junctions replacing a single junction. I can change the external flux and I sort of change my external Josephson energy. So what I can do is change the height of the barrier I showed you before. So we can do that by tuning this split ring biased by one external flux. So you can start to play with combinations of all these devices in order to see something that can be controlled and used in a sort of memory chip. Okay? Now, phase qubits and transmitters. Another thing, you can again think about that Josephson junction biased by a current, but in a way that the time I make all my operations are much, much shorter than the time it takes to tunnel out of this metastable minimum. And then we can play with this guy here. Again, with a sort of constant current, fluctuation of this constant current, and then we have these two microwave turns for this exciting this system. And again, I can go to the rotating coordinate system, and then again something very similar to what we do in NMR. You go to the rotating system, then we can talk about sort of Rabi oscillations and things like that. And again, the system is very similar to the one we saw before. I'm really talking about these two lowest lying states in this case. Okay. But if you don't want to play with systems, then you have to rely on the lifetime of these metastable states. You can also apply the same sort of physics to a junction where you have, beforehand, we had this Josephson jump energy much larger than the capacitive energy. But we can make something different. We can just make, okay, that's still larger, but not that large. And then we can think about the all that sort of description of the energy levels of the junction in terms of this gate number. But now what I have is this M, which is related to the band of energy. And these guys are the so-called transmitters. Then we can think about this tape for this value here, and 0, 1, 2, 3, etc. And these are the energy levels I have. And again, for initially very close to the origin, these guys are very close to the harmonic levels, but now I have I have always an anomalicity that will give you this sort of dependence. Okay, so these are all candidates for qubits. I can always play with one of them and choose. I can try to improve the conditions for the operation of one of them. I can try to do the best I can. One of them, depending on the facilities you have, or even the choice. There are many competing systems to be good with this. Not only from what I'm addressing here is the superconducting community approach. The thing is that we have many other quantum optics, atomic physics, and people from many other fields are disputing and trying to create new sort of systems that will respond and will be appropriate to be used as theory. So in this case here, as I showed you, we always playing with two-state systems, either with flux qubit, charge qubit, transmons. We always aiming at two-state systems. And two-state systems and the environment is really that thing I told you about, which is the spin Boltzmann deployment. That's the most general thing that we have. But of course, I don't want to use the spin Boltzmann in the full spin Boltzmann. What I want to do is really to try to concentrate on a region where it's useful for me. And that's the one that we have very low bandwidth. You remember when I showed you the phase diagram for the spin boson? We had regions where you had, for instance, complete blocking of the bistable state. I don't want that. What I want is something that oscillates between one state and the other, because that would be a would-be bit. And so what I want is this sort of a system-dominated regime when we have the splitting much greater than this alpha KT. And this alpha is basically the dimensionless density. So we have two times here, and that's the relaxation time, and this is the dephasing time. And that's the dephasing time I showed you. Remember that I wrote an equation of motion for P. That P was the average value of sigma z. So that was exactly the position between one minimum and the other in that degenerate system. And so in this case here, what we have is this is the typical time for dephasing. So in general, what we have is a sort of qubit Hamiltonian, and now couple that to the path of oscillators to have something like the spin boson Hamiltonian. But now I know exactly how to play with that. And of course, I have to do much more than I've done. And one has to be to work on that and to change from one description of a two-state system to another two-state system, and then we can parallelize the system. And there are many technical details. Of course, I won't address them here. And but that's the sort of thing that we have. We have this relaxation time, the inverse of this relaxation time, and this dephasing time and one. And these are the generalizations of this guy for many of these two-state systems. And again, so more experimental results, for instance, for the Cooper Bear box. Again, two-state system, and we have all these sort of circuitry, and we can control that. We have external microwave pump, and so we can repeat everything I've done before with the flux. I'll put it to the charge qubit. And so we have, for instance, this run isolation, and we talk about Gunzig-Friedel experiments and so on. So we have this, again, jumping from one side to the other, we have this oscillation, and there is that. Of course, but there is incoherence in this oscillation. And we can also have this sort of behavior here, different pulses for the system. These are the numbers that we can apply. And you see that we operate at very, very low temperature. All these things. The problem with superconducting qubits is the temperature you have to operate. Usually at a very, very low temperature. And more is excited current bias junction. So again, that's the one that we play with these metastable configuration, and then we can find this basically. Again, as I told you in the very beginning of the lecture, I'm not really trying to explain you all the details of this experimental setup. I'm only trying to show you the direction these experimental results are taking us to. And that's exactly the thing that we can apply. We can use these systems as generally non-mechanical systems, and we can also control the effect of the external world. So now what we have here is transmon qubit, and again, that's the picture I showed you. We still have capacitive energy less than Josephson energy, but not much less. And then we can really talk about non-harmonicities. Okay, now, all these proposals for qubits flux qubit, transmon, and all that, we can see what happens. For instance, with these sort of T1, T2. Remember, T1 is the relaxation time in a sort of NMR experiment, and T2 is the phasing time. And so what we want is to increase this lifetime. And then we see that along the years how it is changing. So people are really improving the systems in such a way that we can have, a very, this is microseconds. Now we're talking about milliseconds, for instance. It can be even many other systems. So that's what we usually have. So that's what people are trying to do, is really to reduce and to improve the coherence time, so we can perform main operations in a very in a longer time scale. And so basically, as I said, that would be a shorter presentation, much shorter actually. And final comments. First one. Importance of properly chosen superconducting systems to study quantum mechanics at system size larger than usual, and that's exactly what we've been talking about, the superconducting devices. Not only them, but they are particularly interesting. And the superconducting devices and so on, but you can have, for instance, bose-Einstein condensates, magnetic systems, many of them. Okay, we've been fairly successful in trying to explain how to control the effect of environments on the systems, and we can always try to improve our architecture of these superconducting devices in such a way that we can use them properly. And so it is something to think about. Of course, that's exactly what people are trying to do. And because, every time we have this sort of thing here, we'll have the second one too. We cannot forget one and just neglect these basic effects. And so, that's another advantage, that we can really describe all these effects of dissipation on these very, very, very complex systems just by using the phenomenological parameter. So phenomenological damping, and we can just use that and have a very faithful description of the realistic system that we have. So we don't really need to go deep into the microscopy of the system in order to describe the effects of dissipation on these macroscopic quantum effects, so to speak. That's more related to my second lecture. So it's nice because this 5-path integral method provides us with a unified way to think about these different problems. You think about time evolution in real time, in imaginary time, to describe the decay of metastable states in the equilibrium, and we made use of this approach here. 5-path integral is quite useful. And it showed us some very powerful results that we cannot get from these usual master equations. And the master equations are valid only. We can show from a very general approach that for high temperatures and any damping, or for very low damping and any temperature. So these are these two extremes where we can play safely with master equations, which is reality for most of the systems. And I always mentioned something which was I didn't have time to explore that much, which was the collective coordinate method. And and also the collision model, both with the fermions in 1D or 1x counterpart. And so we can use that to play with topological excitations in material media. Like, for instance, the vortex lines, we can use that, or you can use the Gauss oscillator still. But you can think about bright and dark solitudes and vortices in Bose-Einstein condensates, skirmons and domain walls in magnetic systems. So we have a very rich spectrum of systems where we can play with these guys here. And even for this modified model of the collective coordinate. So as I showed you, sometimes you have to do something else in order to describe the system instead of only the Gaussian approximation, which is basically the result that we get in the battle oscillators. Sometimes things are not so simple. The battle oscillators, as I told you, is very general, but it's not the most general thing there is. We can always end up with something much harder to play with. And experimental organizations, vortex dynamics in 2D superconductors, superconducting devices, etc. Okay, that's what you can get from these systems there. We can project some sort of very specific systems where we have some sort of specific quantum mechanics when we apply these systems there, and that can be quite useful. And these are relevant for testing quantum mechanics at the macroscopic level. It has to do with the foundations and quantum theory of measurement. So many people with this dispute of, okay, measurement, does it make sense or not? And the collapse of the wave function, people start to discuss that in many, some groups, and we started to think about decoherence. Many people start to say, well, that's the solution for the measurement problem. And some other people claim, no, they not even grasping the solution. So there is a sort of very long-standing dispute over the problem of quantum measurement. But that's the way that people feel very comfortable sometimes about the measurement question. That you can really reduce, a quantum mechanical superposition to a sort of mixed state description within a very, very short time. And so many people are happy with that. Some other people are not. More. Of course, improvement of the coherence time, in technological applications, quantum computing, quantum information security. That's exactly what I showed you at the very end. People trying to improve the coupling of the system or the design of this qubit in order to be more efficiently coupled to the environment, to what you need. And more recent applications of that, quantum engines and quantum thermodynamics. Of course, we're talking about the thermodynamics of something which is very small, nano systems, and we're trying to see what happens at this crossover between microscopic applications, microscopic approach to the system, and something which is more macroscopic, namely thermodynamics. So in the middle of the road, that's exactly what you're talking about, right? All the time, from the very microscopic quantum mechanics is there to the macroscopic, then we are in Noah's land. Noah's land. It's right in the middle. Then we're talking about dissipation, then quantum mechanics at the same time. Otherwise, we're playing only perturbation theory. But now we say that. All I've been saying is actually about this competition. And now it's really properly designed to deal with systems here. Right? And crossover from thermodynamics to the statistical mechanics. Right? So, and of course, much more to say, and then other applications omitted either for the lack of time or ignorance of the speaker. Thank you very much.
Thank you, Professor Amir, for accepting me here and your lectures. So, questions?
I was wondering if you could expand a bit on the first point about the quantum theory of measurement. I mean, what would you expect to investigate or test and to find out something more about the problem of the wave function collapse?
Let me get the microphone. Okay. Everything that has been done can shine some light on this process. Of course, people are creating different systems and trying to make a genuine model for, not genuine, but some more controllable model of a measurement apparatus in order to say, okay, now we have something I can really think about as a sort of measuring device for my system. But you know, it's always the same sort of description. You're talking about pointer bases, you're talking about some sort of uncontrollable degrees of freedom of this box. And then you have an external system. And of course, you can only say that we will have the entanglement of the system and the pointer operator. But then you get rid of all this mass of the environment. Again, you will say that I reduce that sort of complicated pure state system of the whole universe and say that I have now a sort of mixture of the pointer and the system itself. So if you think about the pointer here or there, and it's a mixture. People are happy with that. Some other people are not. Say, no, it's not that. The postulate collapses the wave function. Something else. That's why I said it's a very long-standing dispute. But all the models I know, they are always based on this idea that you can make a complex pure state system and your measuring apparatus is composed by some pointer bases, some operators that will couple to my system, and some junk you have to get rid of. And again, sometimes they have very nice models, etc. Say, no, I have solved the problem. That's only a model, but the bottom line is that one, that you still have the same sort of physics. So that's what I've seen so far. In the end, you can always reduce that to the idea of the coherence and if you want to address the question of merit.
Thank you.
Amir, thanks for the lectures. Just that part you were talking about creeps and inverses and that graph you show about the quantum creep, that as it goes down, the temperature, you reach a region. So what is the difference? Because I maybe have lost the explanation between the lines. Like you have a line that has a more that stabilizes. If I'm right, it's like resistivity of temperature.
No, what happens is that when you have high temperatures, that line will leave the configuration very easily. Just by thermal fluctuations, you can distort that line to go to the next configuration, the next one, and that's a sort of avalanche. It's a flow of lines, and that is a very highly resistive state. On the other hand, what you can have is that your lines end. At this time, you have very low temperatures. So it will take a long time to hop from this sort of configuration to this one. So that's the creep. Now it stays there for a long time, then you start to tilt the potential just by an external current, so Lorentz force, and then we start to pull the line with the Lorentz force, right? And now it's hard for the particle to leave. It will not flow, right? Because there is a barrier. And what happens is that it will hop to the other side quantum mechanically. By that same sort of a mechanism I told you about is a quantum mechanical nucleation problem. Right? Take part of the line, tunnels. So a very large portion of the line will tunnel to the other configuration. And depending on this size, it either expands or shrinks. When it shrinks, it goes to initial configuration. Then it can also expand. Then you have the whole line coming to this point. So that sort of production of the critical length is due to quantum mechanical tunneling. And that's why I'm claiming that it's completely temperature independent. Right? It depends only on the height of the barrier, and so that's another thing. And of course the elastic term is important there too. Because that's the competition between the volume or length, energy, and the distortion of the walls of these lines.
Okay.
But then you freeze this lifetime of the line in that configuration. As you go on increasing the temperature, you will start to shape this line into a hot piece. Actually, even by thermal activation, you also create this critical length. But now it's the only thing that is different is the mechanism. One of them you create critical length just by hopping. Sorry, just by going over the barrier by thermal fluctuations. And the other one, you cross the barrier. It's just a finite length that will cross the barrier. It's simple to explain in the picture of the tunnel itself.
So in certain scenarios, we are, sorry, had you finished to answer?
Sorry?
Had you finished to reply?
I think so, yes.
Okay. In certain scenarios, we are interested in the single trajectories of some dynamics, right? So we're not looking at the evolution of the density matrix, which is kind of the average state over different trajectories, like still in the context of open systems. We want every single trajectory because it can hide some information. I'm thinking about measurement-induced phase transitions, but there are other scenarios. And for example, to study these systems, we use a stochastic Schrödinger equation. And I don't know, maybe it has nothing to do with it, but I was wondering if one can use this path integral formulation to derive this type of equations, or probably from your face, probably else, you know.
This stochastic, well, okay, sorry. This stochastic,
So essentially,
you want me to tell you whether I can induce some sort of Schrödinger stochastic equation from the path integral formulation.
and somehow it feels natural as, like, maybe it's like my imagination, but I would imagine that you can interpret the path you're integrating over as the possible trajectories the environment is inducing in the system, and you can look at the single trajectory, and instead of averaging over the trajectories, you first look at the property of the single trajectory, and then you apply the average.
The origin of this path integral formulation of quantum mechanics is the so-called Wiener measure, right? And Wiener measure, that was back in the 1930s. This guy, he proposed a sort of measure that will allow you to take, for instance, to look at a particle from the origin time t. But that's a sort of Brownian particle classical, right? That would just take the trajectory, and then you start to ask what's the probability of being a sort of window at time t across that region, and then the next one. So you end up with the diffusion equation. So that's exactly the Einstein model for classical Brownian, right? So you get it. But what you get there is the diffusion equation. Instead of Schrödinger equation, it's a diffusion equation. So what you have to do in that case is to say that you play with imaginary time. So go the other way around. And then when you do that, you find, instead of finding the density, the probability density, the conditional probability density to leave this point, get the other one, so give the minimum, what you have now is the propagator. So you replace one thing by the other. And so you no longer have a conditional probability, but what you have is the propagator from one point to the other. So you change it, and the picture is exactly the same, right? You use inner measures. And like I say, what I have to do now is to play with both. You want me to say, no, stay in real time in quantum mechanics, so that imaginary times infinite are better. And then you say, fine, now let us get some sort of stochastic behavior for my Schrödinger equation through the final path summation. Well, I don't know. You can do that if you really couple two systems and say that you have the force acting on the system is something like a white noise. But now, what I'm doing, I'm going back to what I told you a couple of days ago, namely the building density operator. So take one history with a force F and another history with a force G. Now you say that these guys have the same force and they are, sorry, they are different, but they are delta correlated. I can do something like that. But what I get is, once again, it's a sort of density operator for some sort of external stochastic picture. But, I don't know whether it gain much. It won't be a sort of stochastic Schrödinger equation. It will be a stochastic motion of a particle, which is in the sort of, which is now a mixed state. It's no longer a pure state, it's a mixed state. Because you're making the average over this force acting on the particle. No problem. But now it's you miss it. You miss your Schrödinger equation. All the approaches I know, in order to get something like that, really pose it, put it in by hand, and then see what happens next. For instance, there is a theory called the Nelson quantization. And in Nelson quantization, you do something like this, you mix up Brownian motion, two views actually of the Brownian motion, Einstein and Uhlenbeck, and then you mix them up, and in the end you create some sort of external pumping that I don't know where it comes from, and in the end you get some equation by a sort of stochastic approach. But that's something else. That's an alternative way to think about quantum mechanics. But and it's related to the, I think it is related to the sort of stochastic Schrödinger equation. Many people try to create some alternative theories using stochastic approach, and
Okay, thanks.
Questions?
have I answered the question? Are you happy with the answer? Not quite. Okay, fine. We can discuss it.
Okay, so Professor said about the coherence coherence time or the relaxing time. And I would like to know if you have other kind of measures or quantifiers which tell us some amount of the coherence which is happening with our system. Or usually is only the relaxing time.
But, no, I didn't quite get it.
Mhm.
What is that? Please
Yeah,
say.
usually when I see the papers which are looking for the coherence in some
Yes.
kind of system, usually we look by the coherence time.
Yes.
So that's the standard measure or have other ones?
Well, the thing is, the coherence, what you want to explain that, is the following. You want to tell me why pure state will collapse into a sort of a mixture. It will lose the sort of quantum mechanical coherence. Right, so you can ask me what are the mechanisms that will give you the coherence. I presented you one here, which is the bath oscillators, and we have damping, and together with that, it's two things at the same time. So just damping in the system will be enough to give you this decoherence as well. And right, and that's called the amplitude damping. By people, for instance, in optics, they would job, amplitude damping, phase damping, so we can really act, for instance, in the off-diagonal elements of the matrix, of the dense matrix, with some sort of stochastic force, and then you can destroy everything. But in this, what I'm doing here, the mechanism that gives you amplitude damping, or this sort of thing here, is more complex, because you have to think about the coupling of the system environment and how it, in the long run, it will correlate your system to the environment. And then, within a very short time scale, you can show that, like you have, if you trace your coordinates, you find that you have a mixture. Right? So, it's something else that involves, entanglement of the system to the environment, and then the second step would be to trace the environment. And then naturally destroy your off-diagonal terms. So that's one thing. That's another mechanism. So you have other mechanisms as well. And, but they all tend to destroy your off-diagonal matrix elements. Now, if you want something else, many people think about, okay, fine. Sometimes people want to invent some sort of alternative multiplication in such a way that, for instance, you can describe self-localization. But that's something else. I don't know what the rest of it is.
Okay, so we have last question here.
Yep.
Thank you very much for the lecture, Amir. And indeed, this is not exactly a question. This is just to tell some history and to make another thank you, a big thank you to Amir. Because this series of conference started in 2007, and when the young guys of 2007 were organizing that dream of them, they discovered that organizing events is a complex thing. And we do mean that you have some real part and some imaginary part in those organizations. And it was essential that in that organizing committee, we had five guys doing the real work, and other two important guys doing the imaginary part. That was really signing things and trusting in the young guys that they would do the correct things when the two senior guys were signing the forms in order for us to have the possibility of doing this or that first event of the series. So this is an important moment to say a big thank you to Amir to be one of the brave guys of trusting in the youngsters and making all those things possible. So, thank you, Amir.
Wow, it's my pleasure. That's all I can say. I've done, I'm really flattered. I wasn't expecting this. nice speech and nice welcome. That's my first time here, but of course, you know, the whole history of the event, and I'm quite proud of you guys that you could really make it work. And okay, I must thank you very much.